Complex functions play a vital role in many fields such as engineering and physics. An example of application that utilize complex numbers is signal processing. In signal analysis, complex numbers are used for a convenient description for periodically varying signals. In the actual physical quantities, it is usually represented in terms of sines and cosine by real functions. Corresponding complex functions are considered of which the real part of the original quantities. For a sine wave of a given frequency, the absolute value of the corresponding z is the amplitude, while the argument is the phase. Using Fourier analysis, representing a real valued signal as a sum of periodic functions are often written as complex valued functions of the form ft equal to ze I omega t, where omega represents the angular frequency and the complex number z encodes the phase and amplitude. In electrical engineering, the Fourier transform is used to analyze varying voltage and currents. The treatment of resistors, capacitors, and inductors can then be unified by introducing imaginary frequency-dependent resistance for the latter two and combining all three in a single complex number called impedance. This method is called phasor calculus. This use is also extended into digital signal process and digital image processing, which utilizes data version of Fourier analysis to transmit, compress, restore, and otherwise process digital audio signal, still images. Another application of complex numbers in electrical engineering is the representation of alternating current. When electrical engineers analyzed alternating current circuits, they found that quantities of voltage, current, and resistance were not the familiar one-dimensional scalar quantities that are used when measuring direct current circuits. These quantities, which now alternate in direction and amplitude, possess other dimensions, which are frequency and phase shift, that must be taken into account. In order to analyze alternating circuits, it becomes necessary to represent multidimensional quantities. In order to accomplish this task, scalar quantities were abandoned and complex numbers were used to express the two dimensions of frequency and phase shift at one time. In mathematics, I is used to represent imaginary number. In the study of electricity and electronics, J is used to represent imaginary number instead, so that there is no confusion with I, which in electronic represent current. It is also customary for scientists to write the complex number in the form A plus JB. Relationship of voltage, current, and resistance is as E equal to I R, where E is voltage, I is current, and R is resistance, which in alternating current refers to impedance. The following is an example for the mentioned application.
Hi everyone. Now I'm going to talk about the application of vector in our daily life. For an example, we can see the calculation of vector in the roller coaster. The launch roller coaster is a modern form of the classic amusement park ride. So unlike its predecessors who rely on a chain lift, the launch coaster initiates the ride by launching the coaster at high speed directly out of the gate. Vector calculus is a powerful tool for those in the business of ride design and creation. Calculus methods allows us to determine the maximum height attainable by a roller coaster before the track is even built. So without this knowledge, a hill could be constructed too high and the roller coaster would valley out. So this term is used to describe what happens when the roller coaster is unable to continue off its path, ultimately leaving the coaster stuck on the lowest portion of the track. Amusement parks lost time and money from the malfunction, such as veiling out, since the coaster has to be towed back to the starting position. So by doing all the appropriate calculation prior to the construction of the ride, it enables the roller coaster to run as efficiently as possible. So to determine the position vector of the roller coaster as a function of time, we use a well-known formula that is a projectile motion. So let I represent the unit vector in the horizontal direction and J the unit vector in the vertical direction. Then the position function is given by this equation. So this is the basically the equation that we use for calculate the vector of the roller coaster. So this is the equation. Okay, so overall, this application of calculus proves to be very important to the field of engineering. When it comes to designing and constructing rides, there are many calculations that need to be done. Without performing the appropriate steps to ensure things will run efficiently, it could not only ruin the project at hand, but cause money loss and danger. Without taking the time to perform this calculation and ensuring they are correct, it is very possible that the roller coaster could crash, valley out, or put the riders in an overly dangerous situation.
The
So I think
next vector
the vector
application is
application of vector is
GPS.
very important in our daily life.
GPS
Thank you.
stands for Global Positioning System. GPS is a space-based navigation system that provides location and time information in all weather conditions, anywhere on or near the Earth, where there is an unobstructed line of sight to 4 or more GPS satellites.
As shown in the picture, here is the backbone of a GPS, known as coordinate system. There are two different directions. First, line X, known as latitude, which is a horizontal line. Second, line Y, known as longitude, which is a vertical line. Horizontal and vertical intersections give us the point of locations, and combining with line Z, which is present sea level or altitude, bring about the most accurate real-time space indicator. These are the very foundation in coordinate system of a GPS.
Adding up the many circles, the parts allow the grids to model celestial motion even without understanding the true elliptical path. In math, orbiting around the circles can be represented as the orbit is equal to r times e to the I omega t, where e to I t represent moving a circle. The grids in that theory though had circles of different sizes and rotation speeds. This is where the other variables come in. The r represent radius and control how big the circle is. The omega represent angular frequency and control how fast the circle rotates around representing circles. Rotating on circles is simply adding up more these terms. When we add more and more, we change an infinite number of circles, we now have what is called the Fourier series of the orbit. While Fourier analysis can create an ellipsis approximation, but it can create really any shape too. The right arrangement of circles can make an orbit in the shape of Homer Simpson's face. So Fourier series can take anything periodic like a waveform and analyze it as the sum of circles. From the unit circle, it also known that circles is basically sine and cosine. Taking these two ideas together, put Fourier series and its more familiar form as sum of sine and cosine representing waveform. Ears make Fourier series to process sound. Inside the inner ear, a thousand of hair itself of varying length. Because the hair is different length, they resonate at different frequencies. For example, long hair will pick up wave with lower frequencies, and short hair will pick up wave with higher frequencies. When a complex sound wave enters the ear, the hairs help the brain break it down into individual frequencies. Instead of the total sound wave, then, the brain is the bunches of simple sinusoid with different amplitude and frequencies, and then combines them to process sounds.